Thank you. Oh. Thank you for the intro, and thank you for the invitation. It is a true pleasure to be here. Well, unfortunately, not physically, but hopefully at some point I'll get to be there enjoying the California sun. So today the talk will be about autonomous systems, particularly how can we provide correctness guarantee, especially safety guarantees for autonomous systems. And to make things a little more concrete, I'll use an example of autonomous vehicles, since it's the kind of autonomous systems that I'm most familiar with. But a lot of things I'm going to say, like all the challenges, I think it will be quite common across many other autonomous systems as well. And the particular autonomous vehicles I want to talk about are those that operate in urban environment. So in urban environment, that means that the vehicle has to deal with pretty complicated scenarios, like some other agents, some other vehicles that violate the right of way. There are vehicles that park illegally, right? And possibly the next intersection that's coming up, we have an illegal park truck that completely blocked our view, right? And with oncoming car that we need to yield for. And so you can see that even with very light traffic, like what you saw in the video, there are already quite a number of interesting, complicated scenarios, like, you know, construction right in the middle of intersection with construction worker walking around, right? So we have to deal with all these complex situations, and many more of this different that it will encounter. Now there are times that things do not go as well as in the previous slide, and let me use the next video to demonstrate the challenges in designing autonomous vehicles or autonomous systems more generally. So this video was from Caltech vehicle, Alice in the Urban Challenge. And I want to use this particular example. This is where she has to perform left turn across busy traffic with the concrete barrier here right after the turn. And you can see that the behavior that she exhibits here is not quite ideal, right? So the intersection is very busy, but she went through very slowly and at some point back up right in the middle of this, right? And this sort of illustrates what I would say like three main challenges of designing autonomous systems, right? So first, uncertainties, right? The system have to deal with the environment that is uncertain, unstructured. And what this means is that there are a large number of scenarios that the vehicle has to handle, right? And in the case of Alice, we have tested merging, we have tested tight turn, we have tested driving next to obstacle, right? We just have not tested all of this in conjunction all together, right? And you can imagine many other scenarios that you cannot possibly enumerate when you test the system. So that's the first point. The second challenge is the interaction. So we have in the system, right, many heterogeneous components. So we have perception, we have planning, control, localization, and so on. And their interactions could be quite complex. And some of this interaction might only lead to bad behaviors only under very specific scenario. Right? So this second challenge sort of tied to the first challenge a little in that because there are so many scenarios, we cannot test them all. So during testing, we might not detect all the bad behaviors that the system may exhibit. In the case of the video that you just saw, there were three components involved in the vehicle. So we have the path planner that plan a path for the car to follow. We have the safety system that would stop the vehicle whenever it deviates too much from the planned path and is about to run into an obstacle. a very typical safety system that you even see in some modern cars these days. And the last component is the steering control. In this case, we limit the steering rate at low speed to protect our physical steering system. And if you think of these three individual components by themselves, right, each of them, they are reasonable, it seems to make sense. It's just that in this very particular scenario, right, they interact in the bad way because the road that the car has to turn into is narrow. What that means is that the planner has to produce a very sharp left turn. And because the car starts from 0 speed, right, the steering control would not allow the car to turn as much. So Alice would deviate a little from the path, right? But because also this concrete barrier, right, the safety system say, oh, now you deviate too much from the path and there's concrete barrier right here. So I'm gonna stop the car, right? And then that leads to even smaller speed, right? So the steering rate get even more constrained and so on. And this causes the car to sort of stutter in this intersection and cannot complete the turn. Right? This would also involve the third challenge, the combination of discrete and continuous decision making. Right? Different level in the vehicle, like planning, control, they work at different level of abstraction. Right? We may have decision planner that only reason at the level of, do we stay in lane, do we overtake another vehicle, and then the path planner that reason at a more continuous level, right? And the steering control that obviously look at the physical vehicle, right? And if this abstraction are inconsistent, like in the case of the three components I described earlier, then bad behaviors could emerge from this. Right. So given that, so still, even though the system is complex, we still want to be able to provide some guarantees, some correctness guarantees. So with this, we look into applying formal methods, right? So in this case, we start with the model of the system, right? So our own vehicle. We describe the requirements. So this is what do we want the system to do, right? Besides this, we also need to have some assumptions about the environment, right? So we might need to assume that other cars to some extent follow the rule of the road and do not try to just run into us, right? Otherwise, we cannot leave our garage. So we need some assumption about what other agents could do. And from this level, that is typically not formal, right? We try to formalize them into the system plus the environment model. This part describes all the feasible behaviors of the system. Right? Some of this might not be desirable. So for example, it is physically possible for a car to run into a person. Right? It's just not desirable. Now on the other side, we have the formal specification. This one formalizes what we want the system to do. Right? So some of these behaviors may not be feasible, right? But they are desirable. So like not running into a pedestrian could be the specification. Right? Now, given the model of the system and the specification, we can, just like in the case of Alice, we can design the controller manually. And then we ask the verification problem. Right, whether the composition of the controller and the system satisfy the specification. Right? And the answer we want to get from this process is either it satisfied, right? In which case we get a certificate. This is like, when we want to prove whether a control system is stable, right? We can have a Lyapunov function, right? And then that provides a certificate for the stability of the system. In this case, we consider more complex properties, but there's the same notion of certificate also. And otherwise, if the spec is not satisfied, the process could give counterexamples. Right? So you can use that to sort of debug the controller. Now, what I think is a more attractive approach is synthesis. So instead of designing the controller manually, put in all sort of hacks, like what we did with Alice, a better way is to ask the question of, can we automatically synthesize this controller, right, such that it, by construction, satisfies the specification, right? Or in case that a controller does not exist, like for example, our spec may say that we want the car to go to the middle of the ocean, right? In that case, it's just not physically feasible, right? So in that case, no matter how smart you are, you cannot find a controller to satisfy this spec. So this is sort of a high-level description of formal methods. Now let me go a little bit into detail of formal synthesis, right? This is where we want to construct automatically a controller that guarantees that the specification is satisfied, right? And I want to describe various formulations for synthesis, right? But instead of going into all the math and notation, let me give a very concrete example. Right, so we have autonomous vehicle here at the lower right corner. Right, this is a system that we are controlling. The car, the autonomous vehicle, want to make an unprotected left turn. Right, there is an oncoming vehicle here that is not under our control. Right, and also a traffic light. Right, in this case, it does not have the dedicated turn arrow. Right, so we are making unprotected left turn with oncoming traffic. So given this system, right, one of the properties that we certainly want to, so we want to describe the properties or the behaviors that are correct. Right, and in this case, we utilize a language called temporal logic, or specifically linear temporal logic. Right, so in linear temporal logic, the basic building blocks are what we call atomic propositions. So there are variables that can be that are satisfied at a given state, right? So here you see H4. This means that human-driven vehicle, right? So H is in cell label as 4, right? So that means this oncoming vehicle is at this cell. Right. A4, so A stands for, in this case, autonomous vehicle, right? So it means the autonomous vehicle is also in C4. Right. We also use typical logical connective like disjunction, conjunction, negation, and so on. Right. So in this case, not H4 and A4 means there's no collision. Right. So the two cars cannot occupy the same cell, right, in one state. So far we only talk about a single state. Right. The idea of temporal logic is that it extends this semantic to allow us to reason about a sequence of states. In this case, it adds temporal operators. One of them you see here, this is called until operator. And what this means is that whatever after until, right, has to hold. So autonomous vehicle has to be at cell 9 at some point in this sequence, right? And before it reach cell C9, right, that there is no collision between the two cars. Right? This is what this formula is saying. If you look into formal methods, then you know that there exists an algorithm to translate this into a mathematical object called finite automaton, right? That is equivalent to this formula. I'll talk a little about this later. So that's the specification. Now let me talk a little about how we could model our system. And depending on how we model our system, we arrive at different problem formulation. Right. So the simplest case is when we know exactly how the environment, so in this case, how the human-driven vehicle and the traffic light would behave. Right. So in this particular case, we know that the oncoming vehicle will just keep moving. Right. So in one time step, it would move to the next cell and so on. And the traffic light will keep switching between green and red. Right, and autonomous vehicle has two actions. Accelerate would bring it to the next cell, and brake will keep it in the same cell. Right. So in this case, we have deterministic system, meaning that once the autonomous vehicle shows its action, right, acceleration or braking, the next state is defined, right, is uniquely defined. And with this deterministic system, we can formulate the closed system synthesis problem. right? And the problem is to compute a policy or a controller for the system to satisfy the spec. Right? So we need to decide at each state, should we accelerate or should we brake, right? So that this spec phi is satisfied. Now, a more realistic formulation is that we don't know exactly how other agents would behave, right? So the oncoming car would move to the next cell, or it could stay in the same cell in one step, right? So we don't know exactly what exactly it would do. So we would formulate a different problem, in this case, reactive synthesis problem. And here we want to compute a policy so that the specification phi, right, this formula is satisfied regardless of what the environment does. Right? So whatever actions the human-driven car or the traffic light choose in one step, right, we can guarantee that the spec will be satisfied. Right? So this is more like a game formulation of the problem. Now, the last formulation is when we know a little more about how the environment would pick their actions, right? In the sense that we can put the probability on each of the transitions, right? So for example, we know that the human-driven car will move to the next cell with probability 0.8, right? And would stay in the same cell with probability 0.2. Right? In this case, we could formulate probabilistic synthesis problem, where the goal is to compute a policy to maximize the probability of satisfying the spec. Right? And we can even extend this formulation to handle the case where the environment is not fully observable. Right? So we might not be able to observe the intent of the oncoming car. Right? In that case, the problem would be maximizing the expected or worst case probability of satisfying the spec instead. So we have these different formalisms in different paper, and if you are interested, you can take a look at this. Now, the major problems with all this previous formulation is that it treats also autonomous vehicles, right? They are subject to many different rules of the road, right? And the problem is that in all the three formalisms that I described, they treat all the rules equally. And it's either you satisfy all the rules, or if you break one rule, it's about as bad as breaking all the rules. Right? So what that means is if you already forgot to turn on your turn indicator, you might as well just run into a person. Right? So that's what the previous formalism would suggest. So to account for unequal importance of traffic rules, right? We propose or we introduce this prioritize the notion of prioritized safety specification. Right? So it includes 4 elements. We have pi, which is a set of atomic proposition. This is like a typical temporal logic formulation. Right? So besides pi, we also compose this atomic proposition into formulas. Right? So in this specific case, I'll use the FLTL. So it's the syntax is exactly like LTL, but it is evaluated on a finite sequence rather than infinite sequence of state. Right? So we have each rule would correspond to one formula in this big phi set. Right? So we have a bunch of rules now. With these two, right, we are still not doing anything different from the previous formulations. In the previous formulations, we'll say that the spec is taking the conjunction of all the rules, and that's all. Right? Now, in this prioritized safety specification, we introduce 2 mechanisms to express the unequal importance of the rules. Right? The first mechanism is that we arrange the rules into hierarchy. Right, so we break the set into n+1 set, right, where the zeros or the very first one is the most important rules. So this is usually rules that involve safety to humans, right, maybe animals also. The second level of the rules could be the safety to properties, right, and then other rules will be less important. The reason we use this hierarchical structure is to express the absolute more important of the rules, right? So what this means is that we would happily violate any rules if it allows us to satisfy the first level rule, right? So if there are no other way, we would prefer to violate rules at the lower level, right, instead of violating the more important rules. So that's the first mechanism. We organize the rule into the hierarchy. The second mechanism is that even within the same level in the hierarchy, right, different rules might have different importance. Right? So satisfying the direction of the lane and being on the drivable area may have different or unequal importance, right? So we have to weight them as well. Right? So we have these two mechanisms, the hierarchical structure and also the weight for the rules in the same level. Okay, so let me talk a little more about this, how would we describe the rules, right? So here I mentioned that we can use a general finite LTL formulas. But as it turns out, you can, if you go through the typical rules of the road, most of the rules are quite simple, right? We don't really need the full power of LTL to be able to express those rules, right? So in this work, we come up with a subset, a subclass of finite LTL, and we call it si-FLTLG formula. Si stands for stutter invariant. Right, so roughly what it means is that the correctness of the formula is not affected by duplicating a letter in a word or removing some duplicate letter. Right, this is very important property when we deal with continuous system. Besides being stutter invariant, we also consider that the formula has to be in a certain form, right? So it's a safety formula. We use the always symbol, right? So from temporal logic, this square means px has to hold for the whole execution, right? And we also constrain px to only contain p, which is a proposition, right? Atomic proposition. We also allow next p, right, where p is atomic proposition, and we allow all the typical logical connective, right? And these are all that we allow to specify the rules that we consider. And even though it looks quite restrictive, we have shown that all the rules in the DARPA Urban Challenge can be written in this form. All right, so I have talked about how we formalize our requirements. Right now, let me get back to how we model our system. Right, so we consider a dynamical system that can be described by a differential equation, x dot equal to f of x and u. Right, and x is the state, u is the control signal. Right, we have the notion of finite time trajectory, right, which is a map from time instance to the state, right, such that there exists a control signal u, right, that satisfies this differential equation. So this is a finite time trajectory. To be able to reason about a trajectory, we also introduced the notion of labeling function, right? So the labeling function takes a state and it returns the set of atomic propositions that are satisfied at those states, right? An atomic proposition, an example would be, stay within a lane, right? So the state is within a lane. So given a single state, right, like a position and orientation of the rear axle of the car, we could determine whether the bounding box of the car is within a polygon that represent a lane or not. Right, so that's the labeling function, right? So it takes a state x and return the set of all the propositions that are satisfied at this state. Right. All right, so now that we define trajectory, we know the labeling function. Let me now go into the notion of finite time word, right? So with that, let me use this picture description because it's much easier. Let's say you have this trajectory, right, that goes from time t equals 0 to time big T, right? So it's a finite time trajectory, right? what we would do is that, okay, so first we determine what is the label at the initial state, right? Let's say this label is L0, right? Recall this is all the atomic propositions that are satisfied. And we would go along the trajectories and determine at which point, at which time instance, this label changes, right? So that means the set of properties that the vehicle satisfies now change. For example, the vehicle might just start crossing the lane boundary, right? In that case, the stay in lane proposition is not anymore satisfied, right? And the property of the state change at that point. So we go through the trajectory, figure out what are all the time instances where the label or the property of the state changes, right? Then we can write down the sequence of the tuple, where the first element of this pair, right, is the label, and the second element is the duration where this label is valid, right? So we start with label 0, that's the properties that the initial state satisfied, and the duration of L0, that's T1, right? And then followed by, we have properties L1, right, with the duration T2 minus T1, and so on. Right? So this is the notion of finite time word, right? It abstracts the trajectories into the sequence of propositions or properties and the duration that the property is satisfied, right? Because eventually when you evaluate your trajectory, right, the actual XY heading state does not matter as much as whether the car stay in lane, whether collision happen, you know. So we abstract the state into the properties that the state satisfied. So now that we define the notion of finite time word, we can define with respect to each of the si-FLTLGX formula, right? We define the level of unsafety, which is also the notion of the amount of violation of rule phi, right? The formula is as follows, right? So we go through this sequence, right, and look at the consecutive pairs of labels, right? If they satisfy the formula, we don't penalize it, right, because it's correct. And recall that because PX only include one next operator, right? It cannot be nested. So it's sufficient to determine the correctness of PX by only looking at two consecutive labels. Okay, so if the pair satisfy PX, then we don't penalize it. Now, if this pair violate PX and it corresponds to visiting unsafe state, we would penalize it by the duration where this happened, right? So the duration of Li essentially. And if it corresponds to taking an unsafe transition, we would penalize it by 1. So this is a very specific form of the penalty. Later in this talk, I'll describe how we could generalize this to other form of penalty if we want. Okay, so now this is the definition for the level of unsafety or the amount of violation with respect to a single rules. Right? And recall that previously we have the weights between different rules, right? So we want to eventually derive, given a trajectory, what is the total violation of all the rules that we have in our hierarchy. Right, so what we do is that at each level we have in this hierarchy, we would compute the weighted sum of the violation of all the rules in that level. Right? And then we compose them into this hierarchy, in the hierarchical structure of the rules. Right? And the way we would evaluate or compare different violation is based on the lexicographical ordering. Right? So that means the earlier the number, the more important it is. Right? So if we have two words, W1 and W2, and already at the first coordinate, right, the violation of W1 is already less than W2, then we don't have to look at other coordinates anymore. Right? We can conclude that W1 is better. That's the notion of hierarchical or lexicographical ordering, and why we organize the rule into the hierarchical structure in the first place. Okay, so now we have all the elements we need to define the problem that we call minimum violation planning. So we are given the dynamical system, x dot equal f of x and u. We are given the label of a goal state, right? So we can think of this as one label or one atomic propositions in the set of all the atomic propositions, right? So there could be multiple states that we consider as our goal. And we also have a prioritized safety specification, right? So we have all the rules, we know how they are organized in the hierarchy. The problem is to compute an optimal trajectory. And what I mean by optimal is the first criteria is we want this trajectory to end in a goal state. Right? So at the final time of this trajectory, at time t, right, the label B has to be within the label of the trajectory at time t. And so that's the most important one. Now, the second criteria is that among all the trajectories that end in a goal state, right, we want to minimize the level of unsafety with respect to this prioritized safety specification. And then the third criteria is that among all the trajectories that end in a goal state and minimizes the level of unsafety, right, we want to minimize the amount of time for the trajectory to reach the final state. So this is what we mean by optimality in this case. So solving this problem sort of involved two big challenges. First of all, we have pretty complicated spec, right? It's not just safety, like invariant or stability as we often consider in typical control systems. It consider traffic rule or rules of the road. And the other challenge is that we have a system with infinite number of states, right? So to be able to solve this, we sort of split these two challenges. So the first thing we would do is we will try to abstract our system into a finite state system, right? And in literature, there are sort of two main approaches for doing this. The first one is to rely on gridding the state space into a finite number of grids or cells, right? And then each cell would correspond to one state in the finite abstraction, right? So that would mean that one state in the abstraction correspond to infinite number of states in the original dynamical system. Another approach, which we call concretization, which I will utilize here, is based on sampling the state in the original state space, right? And build this abstraction based on these sample states. Now, to make sure that the abstraction is consistent with the original system, we need to make sure that this abstraction can be simulated by the original system. Right? What that means is that if there exists a transition in this abstraction, right, there must exist a control signal in the original system that mimic this transition also. Right? So this is the notion of abstraction and simulation. And the reason we decided to go with this concretization is that there's quite a nice result from motion planning literature. Right? So it started with the idea of RRT, right, where we keep sample the state in the state space. Right? The problem with RRT is that it cannot guarantee asymptotic optimality. Right? So even though you let the system run for a long time, right, it might not converge to an optimal solution. Right? So in this case, we utilize a new algorithm called RRT star. I think it was introduced about 10 years ago by Tichakorn and Emilio Frassoli. And it fixes this optimality issue of the original RRT by ensuring the graph connectivity. So they show that by ensuring graph connectivity, we can ensure also asymptotic optimality. That means that as we keep sampling the state space, right, and build our graph, the optimal solution in the graph would converge to the optimal solution in the original system. Right? And the algorithm is very similar to the original RRT algorithm. The only change is that instead of connecting a new state to the nearest neighbor, it would consider all log n neighbors and connect to the best one based on the cost to come. Right? It also consider rewiring these all log n neighbors to go through the new state, if that would improve the cost to come to this state in the O log n neighbors. Right? And so the idea is that we want to maintain the tree structure by eliminating non-optimal edges. Right? So, but we want to make sure that rewiring happen so that the edge that exists, right, is optimal. Right? This is the process that did not exist in the original RRT algorithm. There's also a variation of this called RRG, where we just maintain the graph. We don't need to maintain the tree anymore. And in that case, we simply connect a new state to O log n neighbor and vice versa. Okay, so now how do we compose all this that I just talked about to solve minimum violation planning problem? Right. So if you come from formal methods, the first thing we would think about is, okay, let's just translate our LTL spec into finite automaton. Right? The problem with that is that the size of the automaton in the worst case is exponential in the length of the formula. And in autonomous driving, we have to deal with quite a large number of traffic rules, right? And if each rule is already exponential in the length, then composing them will give us this state explosion problem, right? So our solution is to avoid this problem. Right? So instead of doing this translation, we instead translate the original si-FLTLGX formula over pi. So pi is the set of atomic proposition. We would translate that into an invariant formula, always p, right, over the product of pi. Right? So here p is just a proposition. Right, so and this always p together becomes just an invariant formula, which is much easier to deal with. Now we don't have the next operator to take care of anymore. Right? And this translation is also quite simple. We replace each instance p in the original formula by a pair of p comma true, right? And we replace each next p with true and p. Right? So now our formula will be over pi times pi. Right? So once we do this translation, we can utilize the RRT star or RRG algorithm to incrementally construct our abstraction. Right? So we would sample a state, determine its connection exactly the same way as RRT star or RRG would do. Right? The main difference is when we compute the weight or the cost of a transition. Right? In typical motion planning, the cost is basically either the length or the time. Right? In this case, we want the cost to reflect the amount of violation of the rule. Right? So what we have to do is, in this case, okay, so we know what is the end time of this transition. Right? So this is just a typical motion planning algorithm. So what's additional we have to do is we need to look at the labels along these transitions. Right? So we start with the label of the first state. We figure out along this transition, right, where the label or the properties of the state change, and mark those time instances. Right? And when we compute the violation subject to one of the particular rule, we can still look at the consecutive label. Right? And if the label, if this pair, right, Li plus 1, satisfy P, so now P is just a propositional formula. Right? If this is satisfied, then we don't penalize it. If this corresponds to visiting unsafe state, we penalize it by the duration. Right? And otherwise, we penalize it by 1. So this definition corresponds exactly to the definition of level of unsafety we defined earlier. All right, so now let me give a high-level overview of the algorithm. We start with the initial set of state being just the initial state, right? No transition, right? No goal state yet. we sample a next state, like a new state S, right? We connect from existing state S prime that is in the O log n nearest neighbor of S, right? And we connect S prime to S. The next step is we connect S to S prime, right? So the reverse edge. Now, if we just want to use RRG, connect mainly just create a transition, right? So connect S prime to S means create a transition from S prime to S. And here create a connection from S to S prime. Now, if you want to use RRT star, if you want the abstraction to be lighter, right, with less transitions, then we will only add a connection if it actually improves the cost. And we also need to consider rewiring. And so the final step is to update the set of the goal state in the case that the new sample state belongs to the goal. Right? And oops, sorry. And we can just keep, sorry, I cannot. One more. Okay, there you go. And we can just keep going through this loop until we run out of computation time. Right? And at the end, we extract the optimal path from this graph that we have. Right? So that's a complete algorithm. And as I said, because this connect can be defined generally, you can have this part as the template of algorithm, right? And then you can define a version of connect for the RRT star and another version for RRG, right? And that would give you the flexibility of which algorithm to use. Okay, so let me discuss a little about the theoretical guarantee we can provide, right? So as in the RRT star or RRG case, we can ensure a symptotic optimality if Px is a propositional formula, right? So if we start with just the invariant property, we can ensure that the optimal solution from the abstraction converges to the original solution with probability 1. The other property we can prove is the computational complexity. Right, so assuming that computing the label is O1, right, then the algorithm has exactly the same computational complexity as RRT star and RRG. Right, so that's O n log n. And because RRT star and RRG has demonstrated to run very efficiently in real time, it's easy to also implement our algorithm to run in real time as well. All right, so that's sort of the theoretical part, right? So they look nice on paper, but typically things that looks nice on paper, when you just blindly implement it, you might not get the very nice result as the paper promised, right? So one of the big problem here is that we are dealing with dynamic environment, right? So what that means is that a trajectory that is optimal at time t, right? It might not be optimal anymore at time t plus epsilon, even the very small epsilon. It could be the worst trajectory ever. Right? This could happen, for example, when the newly detected objects show up, right? Or a real case that actually happened and caused the first accident between two autonomous vehicles is that a vehicle that is initially parked, right, start to move off while autonomous vehicle is overtaking it. Right, so you can see in this video, right, originally the optimal trajectory is to get back into the lane, but then the parked cars start to move, and so getting back into the lane would be one of the worst thing you want to do, right, because that would lead to a collision like what you saw in this video. So by applying minimum violation problem, and because it's quite efficient, right, we can do real-time replanning, right, in response to quickly changing environment. So we keep evaluating our environment and keep adjusting our trajectory. Right? So to some extent, this approach is better at handling unexpected or unmodeled environment compared to other synthesis techniques like reactive or probabilistic synthesis. So and to be able to sort of enjoy this benefit of real-time replanning, right? One of the properties we want to ensure is the richness of this concretization, right? So the richness of the graph. We want to make sure that we maintain many different options in the graph, right? Instead of just the optimal one, because the trajectory that is optimal now may be the worst trajectory in the future, right? So we want to make sure that the options in the graph is diverse. And we don't have the infinite time for the system to converge to the truly optimal solution, right? So we have limited computation time. So instead of having to reconstruct the graph every time the planning cycle run, right? We maintain the graph from the original, from the previous iteration, right? But we need to update our initial state to correspond to the current state. And we update the transition cost based on the current state of our own vehicle and also the most recently observed environment. Right? So whether the parked car is moving or not. Right? And in practice, RRG-based algorithm would be more preferable, right? Because RRT star only maintain optimal edges, right? But optimal edges at time t might not be optimal anymore at time t plus epsilon. So RRG is often better in this case in practice, even though it needs more time to construct and maintain. So the last thing I want to mention in terms of the practical issues is, so originally I defined a very strict definition of the level of unsafety. As it turned out, the algorithm that I just presented, it admits other definitions of rule violation cost as well, right? The only restriction that we have is that the cost has to be split invariant. What it means is that the cost on a trajectory has to be written as a function of the cost on the sub-trajectories. In our previous specific case, it is a simple summation, right? So the cost on a trajectory x is the sum of the cost on its sub-trajectories, right? And this additive cost would satisfy this assumption already. And also different rules may have different definition of the violation cost also. There's no need to make sure that they are exactly the same. Right, so additive cost, as I presented earlier, this is probably the most common, but we have also considered another type of cost that we call the max cost. Right, so in this case, the cost of the whole trajectory would be the max over the cost of its sub-trajectories. Right, and this particular form is useful, for example, when we want to maximize clearance from obstacles. Right. And the issue that we found in a little hard way is that depending on the cost structure, right, if we have the mix of max and sum, this could break the Bellman optimality principle. And then the traditional graph search algorithm, so Dijkstra, A-star, all these algorithms would fail to find an optimal solution. And so because of that, we recently published another algorithm, we call it iterated A-star, to ensure that when you have a mix of max and sum as the cost structure, we can still find an optimal solution from the graph. All right, so that's sort of things that we put on paper. Now let me show a little bit of some simulation results. This was implemented in Tulip. So Tulip was the toolbox that was developed at Caltech, and I just shamelessly implemented on top of that. All right, so in this case, we consider this blue car. This is an autonomous vehicle. This red car, think of this as a parked vehicle, right? So it's illegally parked next to solid yellow where the vehicle is not supposed to cross, right? Around the parked car, we have this clearance zone, right? So it's the zone where the other vehicles should not get in, because otherwise it would be too close to the parked car. And we consider 4 different rules. So this is a very simple example, right? The most important rule, which is the only rule in the top level, is no collision, right? We don't want to collide with the parked car. The second level has also just one rule, right? To ensure that we stay on the road. We don't want to go off road to overtake this car. The third rule is that we don't want to get too close to the parked car, right? So we don't want our footprint to overlap with this clearance zone. And the fourth rule, which is at the same level as the third rule, is that we want to stay within lane. And for simplicity, I use exactly the same weights for the third and the fourth rules. Right? So you can see that as the algorithm progresses, this is at the end of the 10th iteration. In each iteration, we add 20 states. Right? So at the end of the 10th iteration, we don't have a very good path yet. But at the end of the 40th iteration, right, it started converging to a pretty good solution quite quickly. And you can see how the cost for each level in the hierarchy reduces. From the beginning, both of the first 2 levels are already 0, right? So it just focuses on reducing the third level, right, which is the weighted sum between not getting too close and stay within lane. Now, we consider exactly the same situation, right? Instead of using RRT star, we use RRG, right? You can see this is with RRT star. With RRG, we get much more, much denser graph, right? So many more connections. The number of states are the same. You can see that, so the solution is slightly different. So in the original case, right, it tried best to stay within lane, right, but then violate the clearance rule. In this case, it does the opposite, right? So it tried to satisfy the clearance rule as much as it can, but then violate the lane. But it doesn't matter because these two, at least the way I define this cost structure, right, they are equivalent. The final costs are also quite close to each other. I think if we just keep running it, we'll get something even closer. All right, so let me summarize the 4 different formal methods approaches when we apply to autonomous systems. Right, so closed system synthesis deal with deterministic system, right? Probabilistic synthesis and reactive synthesis, right? So one deal with probabilistic system and the other deal with sort of non-deterministic adversarial setup. Minimum violation planning, we deal with deterministic system, right? But we rely instead on real-time replanning to respond to changes in the environment. Right? In this case, we want to minimize the amount of violation. Right? In the other cases, like in closed system, we just want to satisfy the spec. In probabilistic synthesis, we want to maximize the probability of satisfying the spec. Right? Reactive synthesis is where we want to satisfy the spec regardless of whether the other agents is doing. Right? So as I quickly mentioned, right, the one key benefit of minimum violation planning is its online at any time nature, which allow it to respond quickly to changes in the environment. Right? Whereas in other systems, right, in reactive synthesis, right, we need to rely on having an accurate assumption on the environment behaviors, right? How the system or the environment could make the transition. Right? And we also need to make sure that the spec is realizable. That means whatever the environment does, there must exist a strategy for our system to satisfy the spec. Right? And probabilistic synthesis rely on having an accurate probabilistic model. Right? So the math looks nice, but if you try to apply this, right, you will find the problem of it's very hard to get a good probabilistic model of the environment. Right? How do we know what's the probability that the pedestrian is going to cross the road or not? And if we get that probability, how do we even validate that the probability is correct? Right? This is still not very clear. And these different approaches have different applications. So that's sort of some past work. Now let me talk or end the talk with some kind of future work. Right? So we go back to the very fundamental assumption of formal methods. Right? So if you recall from the earlier slide, right, formal methods rely on having a formal model as well as the spec of the system. Right? In many cases, this is not quite the case. So let me talk about the specification side first. Right? And let me give you this very specific example of, again, overtaking problem. I sort of spend a lot of time on this. So one option of the autonomous vehicle, right, is to, again, violate the lane rule, right, but give enough clearance to the parked car. The second option is that it try to squeeze within the lane, right, but that would mean it would violate the clearance rule. Right? The question is, which of this behavior is true? Right? And how do we even put all these rules into the right hierarchy? Right? So that's one of the first challenge. How do we formalize each of the rule? What exactly does it mean for a car to stay within lane? Right? I originally started with this very simplistic assumption, right? That okay, we have the footprint of the car, we know the lane geometry. Right? Stay in lane just means the footprint is within lane. Right? Obviously, this simplistic view of the world is not quite right, especially in Singapore where the road is quite narrow. You'll see that the bus all the time, it will not stay within the lane. So its footprint just cannot be within the lane boundary. Right? But if you ask anyone whether the bus violate that lane rule, right, people will say, no, they just drive as good as anyone could drive. Right? So formalizing individual rules as well as how what is their importance, right, is still quite a question. Now that's the specification side. The other side that is as challenging is how do we model the system, right? Now that so typically this autonomous system, right, would consist of the perception side, right, and then the planning control that the talk focus on, right? And we speak very different language, right? So nowadays, many of this perception component relies on machine learning approach. Right? And typically, the kind of metrics that you get out of this approach is like precision, recall, and all this. Right? How do we combine this knowledge of the machine learning component, right, to model the complete system or the input to our formal methods component? Or what if the whole system, right, is built using end-to-end machine learning? How do we even model this complete system? Right? That's also quite an active area of research. And another problem I also want to mention, this is the combination of the two, so the model and also the specification. Right? There's an argument that because autonomous vehicle is safe, it is cautious, so it should improve the safety of the transportation. Right? So that might be true if you consider just accident caused by autonomous vehicle itself. But because the way it drives could be, I mean, if you look around, right, there may be a number of people who don't follow traffic rules strictly. Right? And now you are introducing autonomous vehicle that try to better follow the rules of the road. Right? Now you are introducing some inconsistencies between different agents in the system. Right? And it's not clear whether strictly following the rule of the road is actually benefit the overall network in this case. Right? So that's another line of research that I think is quite interesting. So with that, I will stop. I'll play this video from Singapore, the nice and warm place, while I'm happy to accept any questions.